So good afternoon, guys. Okay, let's continue. Hope you guys are doing good. Let's continue the discussion on C programming, embedded C programming. Um, the interface has changed and taken by surprise. So just looking at the Google Meet interface, there is they have changed the interface. So activities, business activities. Okay, this is fine. Chat with everyone. Okay, here we go. Okay, yeah. Okay, so I have to share the screen. I think this is screen sharing. Okay, nice interface by Google Meet. Yeah, okay, here we go. Okay, we have to put square here. Okay, that will be here. Okay, yeah, somebody is on the line. Okay, guys, in today's class, we'll write a few more programs. Let us write some more. You can give it a try. I will not be able to look into all the programs. At least a few programs, just to understand, the significance of C programming, embedded C programming. Okay? Because ultimately we may end up writing code in both the um, what is this? Just a second. Yes. The interface has changed now, so to avoid mirroring, don't share your editor screen or browser window. Here, just a tab or a different window. Okay, mirroring. Okay. That's fine. That's not an issue. That's not an issue. Okay. So what the Google has to say is that sharing. Okay, do that in that case. Share only the window. That is which. Okay. Yes. Here we go. This is what the suggestion by the Google Meet. Yeah. So if somebody is online, it will automatically admit. Uh, okay. Okay. Yeah. Okay. So we'll take few sample programs and we'll execute this. Let us not go into detail. There are many programs in this document. You can find many programs, embedded C programs. So you can try writing the equivalent assembly code as well as the C program. Okay, so that way you can get familiar with the programming. Okay, okay, I'll take some. Okay, so some sample programs. There are many to okay to work with. Okay, let us take this program. Let us understand this program and execute and let's see how it's going to work. Okay. Yes, here we go. Because the interface has changed, I'm scared. I'm not doing any wrong step in any of the window. So that's why I'm okay. Here we go. Okay, so the program is to toggle the a bit of a port or the complete all the 8 bits of a port continuously with some delay. Okay, continuously toggle with some delay. Okay, so delay value is specified using for loop. So for loop, we know that is a conditional executing function. function in C language, where we can run set of lines, set of programs or set of lines uh, with a some condition, as long as the condition is satisfied. Okay, in this case what we have is that the for loop does not has any instruction. Okay, it ends with a semicolon. That means the for loop continuously runs till it goes from the variable goes from 0 to 40,000. Okay, it increments every cycle is going to increment. So till it reaches 40,000, it's going to execute the for loop. So that way the time spent in executing the the no, for loop generates a delay. So, okay, so initially the port P1 will be set to 55H. After some delay generated by the for loop, there are different way of generating the delay in 8050 microcontroller. That is, we'll discuss in the timers in the next topic, next chapter. But in this coding, we use the programming method to generate the delay. The other method is the timer method to generate the delay. So using for loop, we are going to generate the delay. Okay. So the P1 is initially set to, for example, 55. You can start with the double A also, no problem, double AH. Okay. So it's going to toggle between 55 and AAH. The other is double AH. Okay, and between that there is a some delay. Let us observe this. Okay, let us write this program and execute and let us see. Okay, I'll take the program. It comes with the comments also. Somehow not comfortable with the comment. There are different way of generating the delay. We can call a function. This also will see. No problem. Okay, a modification of the program. Um, let's go to the compiler. I'll remove the program. Yeah, here we go. Okay. Take the comments written for out, because that should not confuse us with the delay size unknown. This is actually this is the reason why I'm not comfortable with this on the line. Just a second. Okay. Where is the okay? So delay size also this also I do. Okay, fine. So to start with this, the I need to okay same area. Um, uh, can it be placed on a possible? Okay, so the header file, which consists of these addresses of all the special function register, okay, and the main function is the first function which is going to be executed by the compiler. Okay, so all these C compilers look for main function. Okay, they're going to declare a variable unsigned integer. Okay, so integer takes 2 bytes. Integer takes 2 bytes. Even in that, unsigned integer, okay, unsigned integer takes unsigned integer takes okay 2 byte location, 2 byte data. It can vary from 0 to 65,536. 536. I'm sorry. 65,535. Okay. It can vary from 65,535. Total number of state is 65,536, including 0. 536. Okay, so the advantage of using unsigned integer is that we can accommodate more values than a signed integer. Signed integer is very less, 32,768. Okay, it's very less compared to um, unsigned unsigned integer. Signed integer can take a lesser value. Here, since we are not dealing with the signed numbers, better always go for a unsigned integer. Okay, for 2 bytes. For for 1 byte we can go for a character, unsigned character, that will say 1 byte location. Okay, here we go. So next we have for loop. This, what does it mean? This for loop, this means nothing but infinite loop. Okay, we can also do this using a while loop, while instruction. I think you guys are aware of, in C language we use this, while um, uh, 1 minus 1, anything works, no problem. Anything other than 0 is true, no problem. Okay, we'll try with both. Okay, yes. So initially P1 is set to um, 55H, and for loop we generate some delay. What is this delay? It's a random delay. It depends on various factors. What are the factors on which the delay depends? That we'll discuss in the next unit. Okay, for time being you assume that this for loop is generating the delay. Okay, because of the semicolon it will execute the for loop till this x is less than 40,000. X is starting from 0. X is initialized with 0. Similarly, P1 is toggled. There is initially P1 is set to this we saw in the last class. That is 55. 55 means 0 1 0 1 0 1 0 1. One's complement 1 0 1 0 1 0 1 0 is nothing but double A H, double A H. So 55 is toggled into double A H, P1, port P1. You can take any port. Okay, fine. Yes, in this case I'll run the program, but I'll get one error. What is that error? Let us see. Okay, save the program. It's a C program, and I'm trying to run on .asm. We'll try that also. Unknowingly if we do that, no, it doesn't generate any error. Why? Because okay, it is running sample, and I copied in C program. Okay, so see, I copied the program here, but the program attached is something else. That's why it's not generating any error. It says it's okay program. In fact, if the you can observe this also. Let us say this file does not has anything. It's empty. When you run the program, it generates one warning. End statement is missing. If you include one end statement, compiler says it's okay. Compiler says if you don't want to write any program, I don't have any problem. Okay. So let us remove this. Remove file. Okay, I'll add this file cprog, which where I have written the program, c program dot c. Okay, add the file, close. Okay, but still this program is going to generate one error. Let us see. Okay, build target. There is an error. What it says is P1. That is in registry 51H. Let us look into the file registry 51.h. The P1 is defined as capital P, capital P1. Okay, but what we have written in the program is small p1. In C language, we know that small p is different, is not equal to capital P. This we are aware. In C language, C is case sensitive. Okay, C is case sensitive, so small p is not equal to capital P, and hence it is generating the error. Okay, so either we can do one thing. We can change here only. We can change this to small p, but it's not a suggested way, because next time, let us say we have changed to small p and we forgot and we use capital P, it generates error. So better to use capital letters for the ports in both the places. It should be okay. Save the program, build target, check for syntax error. Okay, that's fine. Okay. Program is okay. Just a second, I need to open the what is that? Spot on clips. Okay, here we go. Okay. So this program now is going to, we're going to run the program. For that, we need to, open the peripheral devices. Not all the peripherals are not required. I had opened your, in the earlier class that to show that four ports can be parallelly viewed. Okay, so let us keep only port P1. Okay, keep only port P1. Yes, what is the initial condition of all the port is? Initially, all the ports are configured as input port. That is, they are set to 1. 1 corresponds to input port. Okay, input port. That is, it is configured as an input port. 0, the port is configured as a output port. Okay, fine. Now, what we do here is that in last class we observed this also. Okay, if we change the pin condition, port condition will not change, because controller is not reading the data from the port, because we are, for that we need to write the program. Whereas if we change the condition of the SFR, that is port in the SFR, the pin condition also changes. This we have seen in the earlier class. Okay, so now let us run the program. Using F11 on my keyboard. Okay, so even if you start from the first line, Okay, so the first line executed is this one, because observe this guys, variable is defined, okay, in text. Somebody's on the line. Yeah, I think I can minimize this window so that um, I don't know whether it's generating the print screen. Yes, it is generating. Just hold on just a second. Okay, yeah, here we go. So, so many windows open, Yeah. Where I was, I forgot. Okay, anyway, so integer variable. Okay, so this integer variable is stored in the internal ROM space above the register bank. Okay, so first register bank 0 is identified. Above that, variable x will be stored, because if here in this program we have only one variable x. Which is defined as a unsigned integer. Okay, fine. Okay, so how to observe this is, let us go to the D memory, that is data memory. Go to 00. Let us see anything exists in the internal memory. Okay, right now we don't see any data here because we are at to assign some value to x. See, we have just declared the variable, we have not assigned any value. Okay, so observe these spaces, observe this port window as well as the internal memory window. Okay, yeah, here we go. F11 on my keyboard. Okay, so for guys, did you check this? Did you notice this? All this content is modified. All this content is modified because the for loop, for the for loop to execute, these values should be stored in the internal RAM space, because variables should be stored in the internal RAM space, and we are declaring x as a unsigned integer. It will take at least 2 bytes. Okay, 2 byte locations in the ROM space. Actually, this will take 2 bytes in the ROM space. What about the internal RAM space? RAM space, what does the microcontroller does is, that is compiler, it will store these values in the internal ROM space. Of course, it is very difficult to understand. It's not that straightforward. It is difficult to understand. Okay, so don't worry. But I wanted to tell you that that both internal RAM space as well as internal ROM space is used to store data and program whenever we write the code in the C program, C language. ROM space consists of both the program as well as data, whereas RAM space consists of only the variables. Variables, arrays, stack memory, something like that. And in C language, we do not use registers. R0 to R7 we don't use. Okay, it's not necessary because we are going to use a variables X instead of registers. Okay, yeah. F11 on my keyboard. Initially, the P1, the port 1 was assigned with 55. Next, port 1 will be assigned with double A. We can see that it's changed to double A. Okay, and again some delay. F11, and say after executing this, since it's a for loop, it will go back to the first line and this will repeat. Okay, so what we do is, I'll run debug run so that we can see the continuous execution with some delay. Okay, you can see that the port P1 data is continuously toggled, changed between 55 and double A with some delay. Okay, fine. So what we can do here is, we can increase the delay. So for example, let us say we can slightly increase the delay to observe the difference. But since x is a unsigned integer, we can go up to, this is 40,000. Maximum we can go up to 65,536. 536 value. Okay. So let us store that let us increase the value. Let us keep it to, let us say 60,000, for example. 60,000. Let us run this program. Debug. Okay. Save the sorry. Not open. Not open. Okay. Save the program. Check for syntax error. Okay. There's one more thing we have to observe is, if the debug session is successful, it will automatically attach a header file to the C program, source code. It will attach. It will attach. It will insert the header file to the source code that is in the project window. Let us run the program. It's now run the program. Straight away full run, because not stepwise execution. Not necessary, because I wanted to show you where the programs are stored, where the the data are stored. I wanted to show you that. Okay, debug run. uh, the delay may not be too much significant here, because this programming method of generating the delay depends on many factors. It depends on compilers, it depends on variable size, it depends on lot many factors. Okay, you can see these locations, it is continuously undergoing changes because variables, the x value changes. Accordingly, the content of the internal RAM space is also undergoing changes. Okay, fine. This is very simple. So next is, let us test out of curiosity. Let us test with the while one, just to make sure, while minus one. But let us see whether um, compiler is okay with minus one. Save the program, check for syntax error, build target. Things are okay because while one, you see, compiler expects some value in while function, so as an argument, it doesn't care what value we give. Okay, debug start session. Again, I'll run the program, continuously run, debug, it runs. Okay, because we know that in while loop, while anything other than zero is a true, only zero is false. That's all. Okay, you can check with zero base, out of curiosity. If you have done in the earlier C programming is okay. If you have not done, you can check. Let us say while zero. There somebody is on the line. Okay. Okay. Let's run the program. Save the file.
Sir,
Yes, yes.
sir, whatever you are presenting, it's only showing the PDF file. It's not showing the key compile.
Oh, okay, okay. Oh, sorry, the key compiler is not showing. No, because I didn't share the key compiler. Sorry, guys. Extremely sorry. Yes, I didn't. Oh, shit. Then I have to. Uh, anyway, I'm recording the session. Don't worry. I'll share the recording. But now I'll share the entire screen. Sorry, extremely sorry. I was actually initially I shared the PDF. Okay, okay, okay. Hmm. I don't know from where to start now. Oh, okay, no problem. Okay, this is the this can you see now the
Yes, sir.
yes, yes, yes. Inform me in the beginning because okay, no problem. Even now it's not too late, no problem. Okay, I guess this was the program. Earlier we had 40,000 here. Okay, 40,000 build target, debug start session. Yes, of course, I'll explain now, but you can look into the video. I'll share it in the YouTube. You can go through the video. Okay. So, what I was discussing was that we need to notice this location, RAM location, and the port location. Okay, and the disassembly window, that is the rom location. Okay, this is rom locations, this is the ram locations. The content of sorry, most content of ram. Okay, and the port, this is the port. Okay, fine. So let us run the program. F11 on my keyboard. This is what I was showing actually. Okay, so initially 55 is loaded into port. Okay, for loop, this was I was talking about. The content of the internal RAM memory changes. Okay, because the RAM space, register bank 0, above register bank 0, it is a variable X is stored. Okay, so accordingly, these values, variable X is stored in the RAM. As I was explaining this, these values are not clear. It's not quite evident. It is difficult to understand what these values and why these values came. This is just for your information. F11 on my keyboard. Initially, it was 55. Now it will be toggled into AAH. Okay, AAH, and there is a delay. There is a delay. This continues. Okay, so instead of running stepwise, I'll execute continuously. Debug run. Okay, we can see that the content of port 1 continuously changes or toggles with some delay. I also showed how to change the delay with some other value. Okay, so let us say, for example, I'll change the delay to um, you know some bigger value, 60,000. For example, maximum value can be 65,536. Let us change it to 60,000. Okay, for example. Okay, in both the for loop, save the program, check for syntax error. Yes, you have to notice that this register51.h header file is added to the source code. If the debug session is successful, if there is any uh, errors in the program, this header files will not be added to the source code. Okay, that's very important. Debug start session. Okay, now I'll run the program continuously, ways, not stepwise execution. Debug run. Okay, you can see that slight increase in delay. Oh, very minute delay. As I was just now explaining, this is not the actual way of generating the delay. Using timers, we are going to generate the delay that we'll discuss in the next unit. Okay, this one thing I discussed, and another thing was that this instead of while loop, the for loop, what happens if we use a while loop, while minus one. Okay, let us check with this also. This is what I was actually discussing. Save the file because I modified the source code. Check for syntax error. Debug start session. Okay, while minus one. So things are okay. While minus one compiler is okay with that. And debug run. Okay, this works. No problem. Okay, as I said, anything other than zero is true. Okay, only zero is false. Let us test this zero. Okay, this was I was about to show you. While zero, debug stop session. Save the code. Check for syntax error. Build target. Okay, so there is already a warning. It says unreachable code. There is already a warning. Line 7 unreachable code. Okay, let's observe this. Look at the warning. Warning is on line number 7. Line number 7 is within the while loop. While is false. Compiler has already detected that while is not at all executable. While loop is not executable because while is false. That's why it's generating a warning, not a error, of course. But now when we run the program, let us see. While zero is a false, this doesn't work. I'm running the program, it is not working because while zero is a false condition. That's it. It's okay. So this is about the toggling of port bits using for loop delay. For loop, or we can use other method of delay also. Using timers also we can do. That will look into that. No problem. Yeah, that's about. We can call a function instead of a for loop. We can define a function with some value. Let me run this program. Okay. So what this program does is it will toggle the bits of a port P1 continuously with 250 millisecond delay. Some delay. 250 millisecond delay is approximate delay. Only if the timer, using timer we can generate accurate delay. Using for loop we can generate only approximate delay. It can be very close to you know um, what do you call 250 millisecond. Yes, I'll take the program. I'll run this program now. Okay, just to demonstrate the usage of functions in embedded C. Okay, to demonstrate to understand functions in embedded C. Okay, yeah. So what the program is doing is a quick look into the program. Um, header file. MS delay is a millisecond delay function. I'm calling a function. I'm defining a function. Sorry, what you call this as there are three things, guys. In the beginning of the class, I told function, declaration, uh, declaration, function, definition. Because there's one more thing. Function call. Okay, function call. That's correct. So with respect to function, we can have three things: function declaration, function definition, function call. This line, second line, corresponds to function declaration. Why we have to declare a function? We have to tell the C compiler that I'm in the program, in the main program, I'm going to use a function called as ms delay. And this delay function, this function in general, takes an unsigned integer as an argument, does not return any value to the calling function. Okay, so this is what is known as a function declaration. This point, there is 13 line onwards, 13 line onwards up to 18th line is called as a function definition. It's called as a function definition. Line number 8 and line number 10 is called as a function call. It's called as a opposite. These things you have studied in theory, C language, no problem. Okay, this is kind of repetition for it. That's all. Okay, revision. So we have a main program, infinite loop. As I said, while 0 is false, anything other than 0 is a true. Again, there is a error, I'll change it, capital P we have to use. Initially P1 is set to 55. It will be toggled into double A with some delay, approximately 250 millisecond delay. Approximate delay, why? Because we are not using timer to generate delay. All these are approximate delay. Okay, 250 millisecond delay, and this continues like this. It continues double A, like this it continues. So whenever this delay function is called, 250 is sent as an argument to the function, which is stored in itime, that is unsigned integer. This itime is used to is used as a variable, counter variable, to run the for loop. Okay, so based on this for loop based on this delay function execution, the delay will be generated. Okay, so what does this for loop consist of? Is, if you see the this delay function, two variables I and j. I will go from 0 to I time, the value we receive from the main program, 250 I plus plus, and for j will go from 0 to 1275 semicolon. That means for every increase of I will go from 0 to 1, j will go from 0 to 1275, 0 to 1275. Next time I will go from 1 to 2. I will increment by one value, it will become 2. The j will go from 0 to 1275. Like this it continues till I goes up to, I reaches up to 250. When it goes to 250, the it will come out of the for loop. It will end the for loop execution. Then the execution of the function terminates. It will go back to the calling program. That is main program. Okay. The question here is, why 1275? Why not 1280? Why not 130? That's the question. The author, this document from where I copied. This author has tested this program on a particular compiler on which this value 1275 has generated a delay of 250 milliseconds. The compiler may not be kill compiler. Compiler may not be kill compiler, because there are many embedded compilers. This author must have used some other compilers. In fact, that is given in the Mazidi book. I don't remember the compiler. I think PowerPC compiler. I'm not able to recall the name of the compiler. On that compiler, with a value of j of 1275, it will generate 250 millisecond delay. We are using kill compiler. With this value of 1275, it may not generate 250 millisecond delay. It will generate approximate delay. So right now I'm not bothered much about this delay value. I want to observe how the delay functions are executed in embedded C program. That's my point of interest. When we use timers, we will be able to generate accurate delay, 250 millisecond accurate delay. Okay, fine. Okay, so let us see the program. Yes, one more thing. What I want to do is, instead of using a port pin, all the 8 bits of a port, let us use only a single pin. Okay, so for that we have to use a single pin that we have to define. Okay, using a S-bit pin, I'll show you that. Okay, using it. Okay, let us define here only, no problem. Okay, so instead of this all the 8 bits of a port, I'll use only one pin. Okay, how to define a single bit of a special function register? S bit. Okay, let us say let us call it as let us use the word toggle bit, TB. TB stands for toggle bit, something else, toggle bit. Okay, because I'm going to toggle this. Okay, the bit is P0 uh, uh, cap is fourth bit of a port 0. Okay. Okay, so I'll, just a second, just give me a second. The bit declaration is bit, okay, something like this. Correct. This is how we declare. You know, yes, bit is the data type which is used to declare the individual bits of a special function register. We have to give some name for the bit. You can give any name, you know, here the author says my bit. You can say your bit, something like that. Okay. How to declare the pin? Okay, say for example, port 2, for example, port 2 has 8 bits, port p2.0 to p2.7, p2.7. Okay, in C program we cannot say p2.4 because dot is a member operator in C language. Okay, this dot cannot be used, and hence we have to use a cap function. We have to use a cap function. Cap is also for a XOR function, but compiler is, you know, will identify, you know, in this case it will identify that it is not the XOR function, it is the identification of one of the bit of a port. That's all. Okay, so we are going to use I'm going to randomly use one a bit of the port. Okay, that is third bit of port 0, some any port you can use. Okay, so what we do now is initially now we have to toggle this bit. Okay, the name of the bit is given as toggle bit, something like that. Okay, so I'll replace this with the that line, toggle bit is equal to 1. That is initially it is set to 1, or let us reset to 0, no problem, because anyway all the bits are set to 1 initially. Now let us toggle this continuously using some delay. Okay, so now this bit should be 1. This bit should be 1. Okay, so what we are doing guys now here is I got the bit p0.3, that is the fourth bit of port 0. This I'm going to toggle continuously 1010 like this with a delay of 250 millisecond in between the no toggling. Okay, 250 millisecond delay. Okay, so this should happen if everything goes well. Okay, I think the program we discussed, we know what's happening in the program. Let us run the program and we'll see what are the different way of observing the, you know, output. There is a different way of observing the output. Let us understand that. Okay, so first let us save the program. Save the program. Check for syntax error. Build target. Okay, things are okay. No problem. Okay, debug start session. Yes. Okay. Debug start session. Here we go. So the port what we are going to use is port 0. Let us go to port 0. I'll let us not look into the disassembly window, not necessary now. This also I'll minimize. Okay, here we go. Peripherals, I'll open port 0. Okay, yeah, here we go. Guys, there is a one more method of observing the port bits, that is called as logic analyzer window. I'm trying to look for. Okay, but debug start session is done. Guys, this is the icon. Can you see this, guys? Analysis window. I think we could have. It's not visible here. Okay, analysis window. Ah, yeah. Look at this, guys. You know, I'm sorry. View. Go to view. Go to analysis windows. There are 3 ways of analyzing: logic analyzer, performance analyzer, code coverage. Go to logic analyzer window. Okay, so it will open. You can see that the window is already open. Logic analyzer window. Click on the logic analyzer window. It is not working. Wait just a second. Oh, it's already open, guys. You know, because it's hiding. You know, that's here. Let me reduce the program, guys. You know, I think I should pull this little down. So the program, anyway, program we know. Let us not look into the program again. This window also I resize. Okay, yes, something like this. I can pull this little down, no problem, so that we can see the waveform. Okay, let us observe the waveform now. Guys, in this case, actually we are going to observe the waveform. There is a bit condition of the port. So for that, first we have to configure the logic analyzer window. Setup, go to setup, select on this. Okay, you can see one dotted line here. Click on this. Okay, the port pin is P0.3. Type as P0.3. Okay, and click on the other white space somewhere else. Now see, though we selected it as P0.3, it has selected it as P0 only. Okay, select this P0 Here select it as bit in display type. Go to signal display. Okay, somewhere here, go to signal display, select display type. Okay, and display type is bit display type. Okay, there are other way of displaying state also, but let us look into display bit type of display. In this display there are one more possibility, there is, you can even select hexadecimal display. Hexadecimal display means it will go from, if it is a 8-bit display, it will go from 00 to ff, if it is hexadecimal display. If it is a normal decimal display, it will go from 00 to 255. This is what you can see on the screen now. Okay, 255. I want, since it is a 1-bit display, I don't want hexadecimal display. Normal bit display is enough. Okay, fine. Okay, that's all the settings. Close the window. Okay, fine. Yes, after closing the window, please observe that, still here it displays P0 only, but it is actually we have selected P0.3. Okay, and since we have selected bit display type, the least the lower end is 0 and the upper end is logic 1. Okay, lower end is logic 0 and upper end is logic 1. So this is logic 0 and this is logic 1. Logic 1. Okay, fine. Let us run the program. Let us run the program. Okay, now, so three things we have to observe. One is the port and the display window, and of course the project, register window. Let us see that. No problem. Okay, debug. I'll run the program continuously. Okay, guess what we see here is observe this port window. This port window, we are toggling only the fourth P0.3. P0.3. What is P0.3? The fourth bit of a port 3. P0.0, dot 1, dot 2, dot 3. Okay. Only P0.3 is continuously toggling between 0 and 1. Okay, that's one thing. And this waveform, what you can observe now is it is continuously toggling, but it is difficult to observe. For that, what we have to do is we have to stop the simulation. Not debug stop session, no. Stop the simulation. Here we can see the way under zoom. Go to the zoom, select all, click on the all, click on all. Lot many waveforms are generated depending on the duration of execution of the uh, program. If you run for longer duration, you'll find lot many uh, waveforms. Okay, so select on a particular point, zoom in. There is a zoom in function. Zoom in. You can see that the port pin has toggled between two lines, logic 1 and logic 0. Okay, that value is displayed as a waveform. Okay, so this we are displaying on a function called as logic analyzer window. Okay, fine. This in oh, sorry, we can do a lot of things on this. We can use these functions. You can see on this top end, there are a lot many functions we can use. Let us say we can use signal information. It gives a lot of information about the signal. Okay, I'll show you that. Okay, show cycles, and you can use amplitude also. It will display the amplitude. You can use a cursor also. Okay, because using this cursor you can measure the time period of the signal. Okay, what is the time period? Is there is one end of this to other end of this. Okay, guys, when you position the cursor on one of the end, you can see that this pop-up window comes up. In this pop-up window, can you see delta on the right hand side? Yes, I'm not able to move. See, if I move the mouse, I'm not able to use the highlighter. Okay, observe this window here, P0. A lot of information are displayed, like mouse position, reference point, time value, program counter, content. Okay, on the last column you can see delta. Okay, in that delta it is showing two values. One is the time period and the other is the frequency. What is the time period? Case time period is this duration. Okay, considering this duration to this duration, which is the total time period of the signal t. Okay, and what is the frequency of this? F is equal to 1 by t. How to measure the frequency? Very simple. Place the cursor on one end of the waveform, that is the rising or falling edge of the waveform, and in fact if you position this it will show the value. Okay, but better to use cursor on one side and move the cursor on the other side. It will show the time period of one complete cycle. Time period is around 1.2 seconds, and the frequency is around 0.7 hertz. Okay, 1 by 1.25 is around 0.7 hertz. So time period is 1.25 seconds, frequency is 0.7 hertz. Okay, fine. Okay, so this is the other way of observing the port pins whenever it undergoes changes, that is toggles. Okay, so let me run the program again, and let us observe the output. Debug run. It is running the program, guys, but how do we know it is running the program? Observe this cursor, guys, it is moving towards left because it is running. Okay, how to observe the execution? Click on zoom on. Click on zoom on. You can see on this side, the waveform is running. That means it is generating the square waveform. Because why it is generating the square waveform, guys? Because we are toggling the pin, that is port 0, p0.3. Okay, initially all the port pins are initially high. Okay, that you can observe from this port window also. Okay, all other pins are initially, in fact, even p0.3 was also initially high. In the program, what we did was, initially we reset it to 0. You can see the program. Initially we have reset the bit to 0. Okay, so from high it went to low. Some delay, it's approximately 250 millisecond delay. Again it went high. Okay, because if it is toggled again, one is stored into p0.3. The p0.3 is high, and again it generates around 250 millisecond delay, and this repeats. So here it's around approximately 250 millisecond delay, and here also it's approximately 250 millisecond delay. Okay, now if you measure the delay using this what do you call this logic analyzer window, we may not get exactly 250 millisecond delay. Okay, as I said, the reason for that is the delay generated using a software methods, that is using these functions, will not generate accurate delay. Instead it will provide some random delay. Okay, for accurate delay like 250 millisecond delay, we have to go for a timers. That we'll discuss in the next unit. Okay, as you can see that, let me measure only the half cycle. There is one end is this I think I need to zoom in further. I'll position this somewhere here. Yes, I don't want this amplitude. I'll remove the amplitude. It is confusing. This end to this end of the, there's only half cycle. Oh yeah, it's approximately, it is generating 627 0.627 seconds. This, what is 0.627 seconds? Is 0.627 seconds in milliseconds. Seconds in millisecond. 627 milliseconds. Okay, what was our intention? To generate 250 millisecond delay. It is generating more delay because this program, now we are running in a kill compiler. Okay, but as I said, this author has run the program in some other compiler. Okay, now how to reduce the delay? Very simple. If you want only 250 millisecond delay only, no problem. Reduce this value 250. Okay, let us keep 250 thing as it is. Let us reduce this to 1275 to some other value. Let us say 500. I'm not sure. Whether 500 gives the exact 250 milliseconds. Just a trial and error. Okay, I'll run the program just to show you that the program that time delay varies as we vary the values in the delay function. Okay, so this by default the logic analyzer window opens up. Since it was just now, it was open. Run the program. It is it is running the program. To measure, for measurement always, what you have to do is, you have to stop the simulation, zoom on, select a point, zoom in, go to very close, closer proximity, so that you can clearly observe the waveform. Select the cursor is now already selected. Place the cursor. Let me zoom in further. No, it's a little too much. Okay, yeah. Select the position of the cursor on this end, and one more cursor on the other end of cycle. It is approximately 273 millisecond now. Okay, what is the value, guys? It was around, let me show you this. Okay, from this end to this end it was 0.273 seconds. Okay, that is 0.273 seconds is approximately equal to 273 milliseconds. Still we are getting high delay than compared to our requirement, 250 millisecond delay. Okay, that means for kill compiler to generate around 250 millisecond delay, This J value should be less than 1275, what it is used by the author in this document. In fact, in the text, in the textbook, author Mazidi, Muhammad Ali Mazidi, he explains very clearly. He says that, the this delay, delay generated using the for loops depends on three factors. Okay, what are the three factors? I'll discuss this in the timer chapter. Okay, I don't want to take up that. I'll mention it here. One is the compiler, okay, and second one is the oscillatory frequency, and third one is the programming language. Even the programming language also affects the delay generate. For example, if this program, if it is written in assembly language program, .asm program, assembly coding, delay will be different. Okay, so these three factors, major factors which will affect the generation of delay using software programming method. This is called as a software programming method. Why software programming method? Because we are using for loops to generate the delay. If we use timers to generate the delay, we'll be able to accurately generate the delay. That I'll take up. Possibly I'll start in the next class. Is that okay, guys? That's okay. In the beginning, I didn't share the compiler. So what I do is, anyway, I've recorded the session. I'll share the recording, on the YouTube. I think you guys know the channel. If you have any doubt, if you want to look into the video again for better clarity, you can look into the video. No problem. Okay. Yeah, yes, that's it. Okay. Yes, there are many more programs. As I said, there are many programs, hundreds of programs which we can't discuss all the programs. There are even see logical, operations also. This you can try it. Yes, use this operators, and check, how the program works. You can observe the output in the code. Okay. As I said, in the C program, mostly these registers are not used. R0 to R7 are not used. Okay, we use the memory locations. We can make use of memory locations or make use of the ports to observe the output. Very simple. Okay, because you may ask a question, why this registers are not used in the C program? Because we know that in the header file, this register 51.h header file, this registers are not defined. Only the special function registers are defined, not the general purpose registers. Okay, so that's why we cannot run the, we cannot make use of a general purpose register to store the data in a embedded C program. Okay, fine. Okay, so many more programs to run. I suggest you to look into this. Any doubt in any of the programs, you can see. We can use a switch case also, just like a C programming. We can use switch case also. Many more possibilities. Yes, many more possibilities. We can use characters. We can use array also. See, we can use an array to store the values. Not many possibilities. Since due to the time constraints, so I'll not be executing all the programs. Okay, so in the next class, guys, what should happen is that, let me open this. There's 2 more minutes, just 2 more minutes. I think this was there in. Okay, here we go. Syllabus. Yeah. Okay, so this is what is this? This a timer. Okay, guys, in the next class, I'll start with the timers. Okay, timers and counters. We spent a lot more time on unit 3 because it's a very lengthy chapter. Earlier it used to be 2 units in the earlier autonomous syllabus as well as VT syllabus. Now, because the processor content was introduced in the syllabus, the contents were jam packed, and we are spending more time on discussing the topics. Okay. Yeah, so next class we'll start with the timer program. Okay, I think I shared all these documents also, this the notes for this chapter. Using that, we are going to continue the discussion. Guess what is the attendance? 50. It was earlier 52. No, now it is only 50. Okay, I don't know. Okay, it's fine. Thank you. Thanks for joining. Okay. Stay home, stay safe, take care. Bye. Very perfect. Recording is here.